From the music you listen to the colors you see, waves are all around us. It's a mind-boggling concept that it's the key to understanding some of the most cutting-edge technology today. Did you know that even the tiniest particles in the universe behave like waves? Before we can unlock those mysteries, we need to start with the basics. What is a wave? How does it carry energy and momentum? Get ready to have your mind blown as we explore the fundamental nature of waves and set the stage for understanding how the world works at its most fundamental level. This video is formed by 3 parts. Part 1. Wavelength represents momentum. Part 2. Frequency represents energy. Part 3. Superposition and interference of waves. Part 1. Wavelength represents momentum. Imagine giving a spring a good punch. It compresses, and that compression travels down the spring, hitting whatever's at the other end with the same force you put in. Assuming no energy is lost along the way, it's like your punch is being carried by the spring as a wave. Now, think about hitting that spring twice as hard. You'll compress it twice as fast, creating a tighter, more concentrated wave. The distance between the peaks of the wave, its wavelength, gets shorter. So, more punch, shorter wavelength. Mathematically, we say that the momentum, the oomph of the wave, is proportional to 1 divided by the wavelength. Shorter wavelength means more momentum packed into a smaller space. We've been talking about pressure waves, like sound waves or the pulse traveling through the spring. These are called longitudinal waves, where the compression or deformation of the spring is in the same direction it's traveling. Think of wind. It's air pressure moving, carrying energy and momentum. But what about those classic ocean waves? The ones surfers ride? These are transverse waves, where the deformation is perpendicular to its travel direction. Ever see a surfer catch a wave? They gain momentum from the wave's slope. The steeper the wave, the faster it lifts the surfer, and the more momentum they gain. And guess what? Shorter wavelengths mean steeper slopes. Again, shorter wavelength equals more momentum. You might think, but surfers get their momentum from gravity pulling them down the wave. True, but the wave first has to lift them up the slope. The speed at which the wave lifts the surfer depends on its steepness. So, the wave imparts energy to the surfer, and the surfer's momentum is influenced by the wave's shape. Still not convinced? Think of those giant waves in the middle of the ocean. They can be massive, but their slopes are gentle. No surfer is catching those waves. Part 2. Frequency represents energy. Imagine you're holding a rope, and you start shaking it up and down. You create a wave that travels along the rope. Now, focus on one tiny spot on that rope. Let's mark it with a red dot. As the wave passes, that red dot bobs up and down. Up and down. If we were to plot the red dot's motion over time, it would look like a wave too. This means that even though the wave is traveling through space, any single point is experiencing a wave in time. The frequency of the wave is the number of complete oscillations, up and down cycles, that pass a given point per unit time. The frequency increases if the speed of propagation increases. The wavelength decreases, or both. For electromagnetic waves, like light, the velocity of propagation is the speed of light, represented by the letter c. This speed, in vacuum, is approximately 3 × 10⁸ meters per second. We can summarize this with a simple but powerful equation. Frequency equals velocity divided by wavelength. Frequency is all about energy. Think back to the rope. To make that red dot bob up and down faster, higher frequency, you need to shake the rope faster. And that takes more energy. Remember how we said shorter wavelengths mean more momentum? Well, more momentum usually also means more energy. We can connect all these ideas with another equation. Energy is proportional to frequency. Now, Remember that frequency is equal to velocity divided by wavelength. We can rewrite this as velocity times 1 divided by wavelength. And since we know momentum is proportional to 1 divided by wavelength, we can say that frequency is also proportional to velocity times momentum. So, to sum it up, energy is proportional to frequency, which is in turn proportional to velocity times momentum. This shows us that waves have both energy and momentum, just like particles. Let's see how this works with light. Light travels like a wave packaged in quantums called photons, and its frequency is related to its energy. Higher frequency light, like blue light, has more energy than lower frequency light, like red light. This is why ultraviolet light from the sun can give you a sunburn. It has a high frequency and carries a lot of energy. The photoelectric effect is a clear demonstration of light's wave-particle duality. When light shines on a metal, it can eject electrons if its frequency is high enough. The energy of the ejected electrons depends only on the light's frequency. The frequency is related with energy per photon, not its intensity. The intensity is related the number of photons. This shows that light behaves like both a wave and a particle. Let's head back to the beach. Ever noticed how waves get taller and closer together as they approach the shore? That's because their wavelengths are getting shorter, which means their momentum is increasing. But wait, doesn't that mean the total energy of the wave is changing? Nope, the total energy stays the same, but it gets concentrated into a smaller space as the wave slows down. This is just a taste of how waves behave in different environments. And it turns out, even the tiniest particles in the universe can act like waves, leading to some truly amazing phenomena. But that's a story for another video. Part 3. Superposition and Interference of Waves. Waves have some unique properties that we don't see in everyday objects. One of these properties is called superposition. When two waves meet, they don't simply bounce off each other like billiard balls. Instead, they combine, creating a new wave that's the sum of both. If the waves are in phase, meaning their peaks and troughs line up, they amplify each other, creating a bigger wave. But if they're out of phase, peaks meeting troughs, they cancel each other out, resulting in a smaller wave or even no wave at all. This is how noise-canceling headphones work. They create waves that are out of phase with the incoming noise, effectively silencing it. When waves meet and interact, they can produce fascinating patterns known as interference patterns. Imagine ocean waves crashing against a wall with two openings. Each opening acts like a new wave source, generating ripples that spread out and overlap. Where these ripples intersect, they can either reinforce or cancel each other out, creating a mesmerizing display of constructive and destructive interference. This phenomenon is not exclusive to water waves. It occurs whenever waves interact, whether they are sound waves, light waves, or even the waves associated with particles. This interference behavior is mind-blowing when we consider particles. It turns out that even tiny particles, like electrons, can behave like waves and create interference patterns. But there's a catch. These patterns only appear when we're not directly observing which path the particle takes. It's as if the act of measurement forces the particle to choose a single path, destroying the wave-like behavior. This phenomenon highlights a fundamental principle of quantum particles: the wave-particle duality of matter. Particles can exhibit both wave-like and particle-like properties, but we can only observe one aspect at a time. This is a direct consequence of the Heisenberg uncertainty principle, which states that we cannot simultaneously know the precise position and momentum of a particle with absolute certainty. The more accurately we measure a particle's position, the less precise our knowledge of its momentum becomes, and vice versa. This uncertainty is not due to a limitation of our measurement devices, but rather an inherent property of the quantum world. It's as if the universe itself resists our attempts to define particles with absolute precision. The wave-particle duality is just the tip of the iceberg when it comes to the mysteries of quantum field theory. If you're curious to learn more about this mind-boggling field, I encourage you to do some research and dive deeper. And don't forget to like and subscribe for more science adventures.